So let's consider one more example. One more example. So look at this now. We're going to find out the limit of x divided by the roots of 1 minus e to the power minus x squared as x approaches 0. So again, we have the same problem as one of the examples we considered before. We have a surd or sodic expression, or say radical here, whatever you call it now, and you have x here. When you make a direct substitution, this is going to give 0 divided by the roots of 1 minus e to the power minus 0 squared, and e to the power 0 is 1, so this is going to be 1 minus 1. This is going to give us 0 over 0. So this expression right here gives us 0, just like as what we have here gives us 0. And again, we cannot use, because it doesn't have any other term written with it, we cannot use the conjugate method here. We can't multiply this by itself to clear this off, because it is not going to change anything. We're still going to have the same expression up here at the end of the day. And if we try or attempt making solving this by applying L'Hopital's rule, we will have something like this. This is gives us 0 by 0, of course. If we try to differentiate this, derivative of x is 1, and derivative of this is going to be derivative with respect to x of 1 minus e to the power minus x squared raised to the power 1 over 2. And let's tidy this up. And this is going to give us the limit as x approaches 0 of 1 divided by, so for this derivative we can differentiate with respect to the core, bring 1 over 2 down, and that will give us 1 over 2 into 1 minus e to the power minus x squared, then to the power minus 1 over 2, then multiply by derivative of what we have inside here. Derivative of 1, that is 0, so derivative of this is going to be minus 2x multiplied by this expression, which is minus of something, so that will become plus e to the power minus x squared. So that is what we get by applying L'Hopital's rule here. So because this has negative power, then we can bring it to the numerator. This is going to give us the limit as x approaches 0 of, bringing this to the numerator, we're going to have 1 minus e to the power minus x squared. So we have just brought this to the numerator, and then it becomes plus 1 over 2 in terms of the power. Then we have 1 over 2 here. This can cancel this off. Then at the end of the day, we're going to have this to be x e to the power minus x squared. So this is what we get by applying L'Hopital's rule. Obviously, we have not changed anything, because still this is going to give us 1 minus 1, which is 0, the square root of 0, which is 0, and it's going to give us 0. It is still going to give us 0 over 0. And if you observe closely, you should see that this is the limit as x approaches 0 of roots of 1 minus e to the power minus x squared, okay, divided by x e to the power minus x squared. So basically, when you make this substitution here, you're going to have 0 over 0 still. This is going to give us 0 times 1, which is still 0. So it doesn't simplify anything. We have not been able to cancel out anything that actually removes the 0 over 0 indeterminate form here. So and you see that even without actually solving, you see that if you differentiate again, that is, if you apply L'Hopital's rule again, this will just come to the denominator. It never vanishes. So there's no way you are removing this expression here. It just keeps going from numerator to denominator, like just swapping this from numerator to denominator, and then it continues that cycle like that forever. So we can simplify this in a number of ways because of the special form it is. But we can observe that the limit of this one here, this e to the power minus x squared, we can break this down. This is just one of those ways. We consider a second way. The limit as x approaches 0 This will be equal to the limit as x approaches 0 of roots of 1 minus e to the power minus x squared divided by x, then multiplied by 1 over e to the power minus x squared. So what have I done? I've separated this into two portions. This is what we have here. Then x is alone. 1 over e to the power minus x squared comes here. So this will be equal to this. And by rules of simplifying limits, we can break this down into the limit as x approaches 0 of roots of 1 minus e to the power minus x squared divided by x, then multiply by the limits of 1 over e to the power minus x squared as x approaches 0. And of course, we know that we don't know what this is yet, so let us write it out. The limit of root of 1 minus e to the power minus x squared, so that's a minus x squared minus x squared, and divided by x as x approaches 0. And the limit of this is going to be 1 by just making the direct substitution. This is going to be e raised to power 0, which is 1 over 1, which is 1. So multiplying by 1, it just doesn't change anything we have here. So you will see that by applying L'Hopital's rule, we have returned to, we have gotten the inverse of what we had here. So we started out with x divided by root of 1 minus e to the power minus x squared. Now we have root of 1 minus e to the power minus x squared divided by x. So we have the inverse of what we started out with. So from this is telling us that if L, okay, we can say let L be equal to the limit, that's the limit of x over root of 1 minus e to the power minus x squared, okay, as x approaches 0. And if that is the case, then it follows that 1 over L will be equal to the limit of this inverse, that will be equal to 1 over L. So if this one is L, then the limit of its inverse will be 1 over L. So it will be equal to the limit of root of 1 minus e to the power minus x squared over x as x approaches 0. By just taking the inverse of this, we get this, the inverse of this. That works because L is not 0. We have seen that from our rules of calculating limits. Now, but what we have here is saying that this limit of x is equal to, this limit of x over root of 1 minus e to the power minus x squared is equal to the limit of its inverse. That means L is equal to 1 over L. And so we can use that to get some idea of what the limit might be. So if this is the case, we're saying that therefore L, okay, is equal to 1 over L. How did we come about that? We just saw that we're starting out here, and starting out here, we were able to arrive at this fact that what we have obtained here was the fact that the limit as x approaches 0 of x over root of 1 minus e to the power minus x squared will be equal to this. So we have seen then that, okay, if this is L, then this will be 1 over L. So this is telling us that L is equal to 1 over L. So if L is equal to 1 over L, when you multiply both sides by L, we're going to have L squared to be equal to 1. And that means L will be equal to the root of 1. This is not an equation or a function. So this is, this is not a function of x that we got. This is some equation. So the root of 1 is going to be plus or minus 1. That means the limit can be plus 1 or minus 1. We don't know what precisely it is. And how do we choose whether it is plus 1 or minus 1? Of course, the fact that it can be plus 1 and it can also be minus 1 already tells you that there's an issue somewhere, and the best guess we can make here is to say that maybe the limit from above is going to be plus or minus 1, and the other one will be it's going to be minus or plus 1, as the case may be. So we're not sure of that from this, but this just tells us that the limit is either going to be plus 1 or minus 1. So We can verify what exactly it will be by checking our calculator to establish that. So this is one of the ways we can make a guess as to what the limit of the function will be. In this case, because it specially happens to have returned to the inverse of the original function we started with. It means that if there was an attempt made to actually apply L'Hopital's rule again by differentiating this again, it will probably, possibly, or most likely result in the given function again, which means that L'Hopital's rule was never going to solve that problem. Okay, so this is the only thing we can tell now. The fact that we know that L is going to be plus or minus 1. We don't know precisely whether it is plus 1 or minus 1. We just know it should be plus or minus 1 as the case may be. Okay, so that is all that this observation could have fetched us. So we have still not solved the limit. So let's find a way to actually solve the limit now. Okay, that is, we're given the limit of x over the root of 1 minus e to power minus x squared as x approaches 0. So from here, we already know from the work we have done now that the limit cannot be evaluated by a conjugate method. It cannot be evaluated by direct substitution because that gives us 0 over 0. We have seen that it cannot be evaluated by L'Hopital's rule because that is going to keep cycling around and cycling around. So then we have to find out another means of solving this. And just like one of the examples we solved before, we can see that this is similar to one of the special limits we've talked about before. We know that the limit of sine x over x as x approaches 0 equals 1. We also said that the limit of e to power x minus 1 divided by x as x approaches 0 was equal to 1. And now we're seeing again that the limit of, we've also mentioned that the limit of 1 plus 1 over x to power x as x approaches infinity was equal to e. So this is one of those things. So out of all of this, the only thing it is similar to here, the only thing this function is similar to is e to power x minus 1 over x. So can we get something like that from this expression? Can we possibly have e to power minus x all over x? So that from that expression we'll be able to simplify this and see how it goes from there. So don't forget that we have here e to power minus e to power x, but here we have e to power minus x squared, and here we have e to power x minus 1. So we should possibly rearrange this so that we have e to power x here and then we have minus 1. So we can easily get that by saying this is equal to the limit as x approaches 0 of x divided by what we have here is going to be the roots of, so we want to extract this expression, so e to power minus x squared into, so if we're extracting this from 1, that will be e to power x squared, such that when you multiply these two, the addition of the powers will give us 0, which is e raised to power 0, which is 1 that we had initially. Then this will now be minus 1. So that is what we are going to have here when we factorize this way. Okay, so we now have something similar to something that looks close to this. The only thing we have left is that if this is e to power x squared and we have e to power x here over x as x approaches 0, then we should try to find x squared in the, since we have x squared power, we should try to have x squared in the denominator of this. So, and how can we do that? The only way we can do that is finding a way to bring in this x. Okay, we can find a way to bring our x into this square root symbol so that we can say something like this. We can say that this is equal to the limit of 1 over the root. So we can say this is 1 over x multiplying the root of e to power minus x squared into e to power x squared minus 1. So we close that bracket as x approaches 0. So what have we done? We have brought the x in the numerator to the denominator, so it becomes 1 over x here. It doesn't change what we have initially. So we can find a way now to bring this into the square root sign. But don't forget something that we've pointed out severally, that the square root of x squared is not equal to x. Rather, the square root of x squared is equal to the modulus of x. So we need to bear that in mind as we attempt to bring this into the square root symbol. All right. So we can say that this is going to be equal to the limit. Just simplifying first, we have root of this root of e to power minus x squared, so we can separate that out. So we can say this is limit as x approaches 0 of 1 over, this is going to be 1 over x still, multiplying root of e to power minus x squared, multiplying the root of e to power x squared minus 1. So just separating these two portions out. And this is going to be equal to the limit as x approaches 0 of 1 over, this is going to be 1 over x multiplying the root of e to power minus x squared. Okay, let me rearrange them now. We'll find a way to bring this into the square root sign. So let me rearrange this and just write this out. Since we have root of e to power minus x squared, we can write that as e to power minus x squared over 2. And this will be multiplying 1 over x into the root of e to power x squared minus 1. And we can simplify this further by taking this to the numerator instead. So this is going to be equal to the limit as x tends to 0 of bringing this to the numerator, the minus sign will be off. So this will be e to power x squared over 2, then divided by 1 over x multiplying the root of e to power x squared minus 1. So that is that about that. So we want to find a way, as we said earlier, to bring this x here into the square root sign so that we'll have it as x squared. But we have to bear in mind that if we're doing such a thing, we have to bear in mind that the square root of x squared is not x. So we can't say that x is equal to the square root of x squared. We know that square root of x squared is equal to modulus of x. So, so what is the next thing to do now? We know that bringing this in will involve us trying to make some comparison with root of x squared. And so the best way to do this is to actually say that this expression here will be equal to, sorry, so let's say this is some equation star. Okay, we'll come back to equation star. But we know that e to power x squared over 2 divided by 1 over x multiplying root of e to power x squared minus 1 is equal to e to power x squared over 2 divided by, so in this case I want to have this as 1 over the modulus of x. I know modulus of x is root of x squared. Why am I doing this? So that we can move it inside the square root sign. But now we have made some assertions now. We are claiming, or some claims, we are claiming that x is the same as root as modulus of x. We know that that is only true when x is greater than or equal to 0. So we have to indicate that this is only applicable, this expression we have just introduced now is only applicable when x is greater than or equal to 0. So if we are going to make that assertion, we have to be clear about it upfront. So then this is going to be this multiplying the root of e to power x squared minus 1. And from here, we will say, let's add another page now. This is going to be, going further, we know that this expression is going to be equal to e to power x squared over 2 divided by, trying to manage this now, this is 1 over modulus of x. I know that modulus of x is root of x squared, then multiplying the root of e to power x squared minus 1. So with this, we say this is equal to, So we can now move this inside the square root sign because this is just going to be equal to e to power x squared over 2 divided by what we have here will be 1 over x squared, the root of 1 over x squared. So both of them will be in, all of them will be in the root sign now. So we can say this is this multiplying e to power x squared minus 1. So from here, we say that this is equal to e to power x squared over 2 divided by the roots of e to power x squared minus 1 over x squared. So we know that this is only applicable for when x is greater than 0. So we have an expression now. And what have we done so far? We have now obtained an expression inside the square root sign that we know that its limits as x approaches 0 is not going to be 0 any longer. Okay. And again, we have an expression outside that we obviously now know that its limit also would not be 0 as x approaches 0. This will not be 0. This will be e raised to power 0, which is 1. So now we are good to go. We can now proceed with our analysis. But we must bear in mind that this simplification is only applicable for when x is greater than 0. So what happens if x is less than 0? If x is less than 0, we won't be able to equate x to modulus of x. If x is less than 0, it is only minus x that we can equate to modulus of x, because we know that modulus of x, of course, which is root of x squared, is equal to minus x when x is less than 0. So let's recognize that this is some equation 1. Okay, we know equation 1 is applicable for x greater than 0. So let's go back to this function or this expression we are trying to simplify. So what happens if x was less than 0? So we now say that e to power x squared over 2 divided by 1 over x multiplying root of e to power x squared minus 1, okay, which is what we have here from equation star that we're trying to simplify. We know that it will be equal to, so we want to get an expression for this for when x is um less than 0. We've got an expression for when x is greater than 0 already. So when x is less than 0, what happens? We will say that, pay attention now, this is equal to e to power x squared over 2 divided by 1 over, so I'm going to have this as minus x. I want to have minus x here. So to have minus x, let me also put minus outside here. Then I know minus and minus will cancel out, so it doesn't change what I have here already. Then multiplying the roots of e to power x squared over 2. Sorry, that's just x squared, not x squared over 2. Then minus 1. So with this, we're going to have this expression to be equal to e to power x squared over 2 divided by, so instead of this, I'm going to have this will be minus 1 divided by modulus of x. I know that minus x will be equal to modulus of x for x less than 0. So I can say that this is going to be applicable when x is less than 0. So that is the idea. That is the way we can work around this. So we know then that modulus of x, again, like we did here, is root of x squared. So we can now replace this and say that what we have is this minus, we can put it to the numerator now. This is going to be minus e to power x squared over 2 divided by minus 1 over root of, sorry, minus is not in the denominator any longer. So this will be 1 over root of x squared, then multiply by the root of e to power x squared minus 1. And from here, this is going to be equal to minus e to power x squared over 2 divided by, this is going to be 1 over, so we can put this together now as root of 1 over x squared multiplying e to power x squared minus 1. Okay, so from here we can simplify further. Sorry. This is meant to be in brackets, please. This is meant to be in brackets. Let's close that bracket. Okay, so avoid confusion, please. So this is going to give us this expression here. This will be equal to minus e to power x squared over 2 divided by, so putting all of this together, the root of e to power x squared minus 1 divided by x squared. So we have another expression, but we know that this is applicable only when x is less than 0. So that is the idea. So what we have seen, or what I have demonstrated to you from this example, is for you to know that we have to always bear in mind that the root of x squared is not x. The root of x squared is actually modulus of x. So whether you are bringing x into a a root expression or you are taking it out of a root expression, you must bear this in mind. We have seen an example of how to have that in mind when we are taking x out, okay, from one of the problems we solved, okay, before now. So now we have seen how to bring x in, bearing in mind that modulus of x is what we have as root of x squared. So now we have been able to see that this expression at equation star that we ended up with at equation star is also piecewise. Is a piecewise. I mean, this function here, so to speak, is a piecewise defined function in the sense that it has a definition that is applicable when x is greater than or equal to 0, which is this, and it has a different definition when x is less than 0. So the difference being that when x is less than 0, there should be a minus outside here. So we must have that in mind. So from these two observations now, so let's call this Roman figure 2, then we can conclude that the expression e to power x squared over 2 divided by 1 over x into 1 over x multiplied by root of e raised to power x squared minus 1 will be equal to this expression will be equal to e to power x squared, sorry, e to power to be equal to e to power x squared over 2 divided by, this will be the root of e to power x squared minus 1 over x squared, and that will be the situation when x is greater than or equal to 0, and then it will be given by e to power x squared over 2 divided by the root of, so this will be minus for the second part where x is less than 0, we have minus outside here. So this is the definition when x is greater than or equal to 0. There's no minus there. That's what we just wrote out. And when x is less than or equal to 0, there will be minus outside. So this is minus something. So we must note that this is going to carry minus. And we're going to have this to be e to power x squared minus 1 over x squared. So the difference being the minus out there. And this is what applies when x is less than 0. So I think we are good to go now. Let me write this properly so it captures everything here. Yeah, so this is the expression we have here. So that means that our function, the function we ended up with up there, is actually a piecewise defined function. So it's a piecewise defined function. It has a different definition when x is greater than 0 or equal to 0, and it has a different definition when x is less than 0. Again, we go back to equation star. From equation star, we see that we are interested in the limit of this function as x approaches 0. So if we are interested in its limit as x approaches 0, since 0 is a breakpoint of the function as we have now seen, then we should evaluate the limit from above and the limit from below. And from that, we will be able to see and compare if the two limits will be the same. So to do that, we'll firstly note that the limit of e to power x squared minus 1 over x squared as x approaches 0 is also going to give us 1. I mean, that follows from these special limits because just like we have replaced in this special limit here, we just replace x by x squared. So if you have e to power x squared divided by x squared as x approaches 0, of course we know as x approaches 0, x squared also approaches 0. So it should give us so that should give us 1. And if we are not completely sure that that is going to give 1, no matter what it is, whether it's from above or from below, you can also solve this separately. So if you substitute here, this is going to be e raised to the power 0, which is 1 minus 1, 0 over 0. And if you apply L'Hopital's rule, derivative of e to the power x squared, that will be 2x e to the power x squared minus 1. Derivative of minus 1 is 0. Forget about that. Derivative of x squared, that is 2x. So 2x is going to cancel 2x. And at the end of the day, when you substitute 0 here, e to the power 0 is 1. So this is going to give us 1 when you apply L'Hopital's rule. So we know that this limit is 1. So when we get here, we just use 1 right here. So then we can say that the limits of our given function f of x as x approaches 0 from above will be equal to the limit of e to the power x squared over 2 divided by the root of e to the power x squared minus 1 over x squared as x approaches 0 from above. As x approaches 0, because we know that that is our function when x is approaching 0 or when x is slightly above 0. So from this, we already know the limit of this expression here is 1. And when we substitute 0 here, this is 0 to the power 0 squared over 2 e raised to the power 0, which is 1. So this is going to give us 1 over 1, which is 1. And if we examine the limit from below, this will give us the limit of f of x as x approaches 0 from below to be equal to the limit as x approaches 0 of minus e to the power x squared over 2 divided by the root of e to the power x squared minus 1 over x squared. So we know that the limit of this expression is 1, so root of 1 is 1. The limit of this expression is also 1, so this is going to be minus 1 over 1, which is minus 1. So we have our result for the limit from below. The limit from above, as we have now seen, is equal to 1, and the limit from below equals minus 1 for the given function. So we conclude again that since the limit of f of x as x approaches 0 from above is not equal to the limit of f of x as x approaches 0 from below, then the limit of f of x as x approaches 0 does not exist. So that is that about that. And we can obviously and expectedly verify this with our calculator, and this also agrees with our earlier observation that the limit could be plus or minus 1. Now we have seen that the limit indeed is plus 1 when it is from above and minus 1 when it is from below, but if we are to take the two-sided limit, it does not exist. So that is that about the usefulness of this observation we made earlier. And like I said, we can verify this limit using our calculator. So let's bring up our calculator, clear of the screen. We have this x, that's alpha x, divided by the root of 1 minus e to the power minus x squared, that is e to the power minus x squared shift e to the power minus shift x squared. Well, what did I just write? Let's clear that. Let's clear that. Delete e to the power minus x squared. Yeah. X squared. Sorry. Minus no, not shift alpha x then squared. So let's calculate the limit. As x approaches 0 from below, so we're going to put in minus 0.00001. So let's see what that gives us. It gives us minus 1, just approximated to minus 1 directly. And if we try to calculate from above 0.00001, that's going to give us 1. So that is that about that. So we already know how to approach this, and calculator just always bails us out. So you know this is always going to give us our result anyway. So if you are dealing with a multiple choice question, you already know you can always just enter this in your calculator and find out what it gives you. All right, that is the end of this lesson. We'll move on from here in the next.